told you I'm going to at least get you initiated into basics of combinatorics today, and I expect you to be at least familiar with the factorial notation. Some of you would have done some combinatorics in school or independently already, but then I will not assume anything except that you understand the factorial notation. Only to that extent I'll expect you to know, and we will try and push hard on the basics of combinatorics. Even while we get on with the business of combinatorics, and we're going to learn a host of things, starting from absolute basics to some very floral stuff in combinatorics, yet I would urge you to stay very free of all of that is being formally taught in combinatorics. The best of issues and the best of situations in combinatorics are those that don't require any formal education. A smart class 7 kid will be able to solve the most sophisticated things, because the most sophisticated things will not require any formal learning, will just require a free head, a head available to act. That is all. Basic logic, basic understanding when to add and when to multiply would be more related to how you've been brought up than what I teach in the class. But then we'll go past the fundamentals and enter into levels of sophistication. Nothing advanced about it, but still we'll try and do as much as we could. And like I might have mentioned in my earlier sessions, that there are two units that would go hand in glove, one on combinatorics and the other one on binomial theorem. They would take juice from each other. While we make some progress in combinatorics, I'll trigger a thread of binomial theorem and then get back to combinatorics. So we will shuttle between combinatorics and binomial theorem, because each one would require the help of the other. So it's best when we do the two things together. Now, first of all, there are two fundamental theorems in combinatorics, two fundamental principles of counting. So essentially what we are trying to learn is how to count. All that we are trying to learn is how to count, and we are trying to learn it in an organized manner. That's what we are trying to do. In the process, two basic principles of counting, two fundamental principles of counting. One, principle of addition. Let's say if there are certain events designated as A1, A2, A3, AN. If there are certain events designated as A1, A2, A3, AN, and let's say the event A1 could take place in N1 ways, the event A2 could take place in N2 ways, the event A3 could take place in N3 ways, the event AN could take place in, well, let me call it AP to not mix up the symbols. The event AP could take place in NP ways. Then the number of ways, these many ways. Then the number of ways in which N1 or N2 or N3, A1 or A2 or A3 or AP could take place is N1 plus N2 plus N3 plus NP. I mean, simple. If there are 5 boys in a class and 6 girls, and you have to select a boy or a girl. You have to select a boy or a girl. Now, so A1 is the event where a boy is selected, A2 is an event where a girl is selected. So it's about A1 or A2. Now, number of ways in which a boy could be selected is 5. Number of ways in which a girl could be selected is 6. So, number of ways in which a boy or a girl be selected is 11. Now, the key word in this is OR. Whenever there is an OR, it generally leads to an addition. It generally leads to an addition. So, that's the principle of addition. And then we have principle of multiplication. In which number of ways in which A1 and A2 and A3 and AP could take place. That's going to be given by N1 into N2 into N3 into NP. And generally would lead to multiplication or would lead to addition. Now, if I say, in how many ways can you select one boy and one girl? In how many ways can you select a boy and a girl? So, 5 ways in which you can select one boy into number of ways in which you can select one girl is 6. So, number of ways in which you could select a boy and a girl is 30. Clear? That's the principle of multiplication. Now, two terms that are widely prevalent, widely used in combinatorics. One is permutation and the other one is combination. When we have a certain number of things and we propose to select those things, we propose to select some things out of those number of things, then there are two possibilities. The order of the selection could be important, the order of the selection may not be important. Now, if the order of the selection is important, then that selection is referred to as a permutation. If the order of the selection is not important, then it's referred to as a combination. For example, if I give you 3 colors, blue, green and yellow. If I give you 3 colors, blue, green and yellow, and I ask you to select 2 of these colors, Now, there could be situations in which the selection would center around the order in which the selection is made. For example, I want to make a 2-colored flag out of these 3 colors. I want to make a 2-colored flag out of these 3 colors. Then 2-colored flag means this is the flag, let's say. Then the flag could be blue, green, green, blue. These are different things. Selecting blue and green and selecting green and blue will give you 2 different modes of selection, right? Or we could have blue, yellow, yellow, blue, or we could have green, yellow, yellow, green, right? In this case, the order of the selection is important, right? In this case, so in how many ways can you create 2 colored flags? In how many ways can you create 2 colored flags out of these 3 colors? 6 ways, right? So this is a case of permutation. And in this case we say number of permutations of 3 different things, number of permutations of 3 different things taken 2 at a time, in which nothing is repeated, in the sense I can't have blue and blue, I can't have green and green. So there is no repetition of the same thing. You know what I'm saying? So then we say that it's a case of permutation of 3 things taken 2 at a time. And how many of these occur? 6. There are 6 ways in which I could create permutation of 3 things taken 2 at a time. If, however, there were 3 students in the class, S1, S2 and S3, there were 3 students in the class, and I want to constitute a committee of 2, then well, whether I take S1 or S2 or I take S2, S1, that will mean the same. So in this case, the order is not important, So I can constitute a committee with S1, S2, with S2, S3, with S1, S3. Yes or no? So how many committees? 3 committees. And in this case, we say it's the number of combinations of 3 things taken, 3 different things taken 2 at a time, again in which repetition is not allowed. You can't have multiple copies of student 1, right? So then we refer to this as, for example, 3C2. This is a case of combinations. So in the event of a combination, the order of selection is not important. In the event of a permutation, the order is vital, right? Now, suppose I have n different things. Suppose there are n different things. Refer to these as T1, T2, T3, Tn. And I want to create a permutation of these n different things taken r at a time. We want to obtain the number of permutations of these n different things taking r at a time. With no repetition allowed. With no repetition allowed, right? So what we do is, we create these spaces, R spaces. This is space 1, this is space 2, this is space 3, and this is space R. These are spaces, right? And now I start to fill out these R spaces with these n different things. I start to fill out these R spaces with n different things, with no space containing more than one thing, right? The moment I fill out these spaces, then the order is already built into it. The order is already built into it, because what thing comes first and what thing comes later is about the order, right? So the order is already built into this selection the moment I start to fill out these R spaces from these n different things, with not even one thing used twice. For example, if T1 has appeared here, it couldn't have appeared anywhere else in a given selection or a given permutation, right? So then, So what we are seeking is NPR, number of permutations of n things taken r at a time, in which nothing is repeated, Now, the first space can be filled out by any one of the n things in n ways, right? The first space could be filled out in n ways. Now, once you have filled out the first space, you are left with n minus 1 things. So the second space can be filled out only in n minus 1 ways. The third space can be filled out in only n minus 2 ways. The rth space can be filled out in only n minus r minus 1 ways. Right? The number of ways in which you could fill out all these spaces, this and this and this and this and this, will give you the number of permutations of n things taken r at a time, isn't it? Each mode of filling out of these spaces with the given conditions will give you one particular selection in which order is important. That means one particular permutation. The number of permutations that you can create is the number of ways in which all these spaces could be filled out simultaneously, with nothing being repeated. Right. So then, that means these are events. So there are R events. This is A1, this is A2, this is A3, this is AR. So number of ways in which A1 and A2 and A3 and AR could be carried out is like N1 into N into N minus 1 into N minus 2 into N minus 3 into N minus R minus 1. That's the number of ways in which these spaces could be filled out with no repetition from these n different things. Yes or no? So then, number of ways in which these spaces could be filled out with the given set of conditions is this into this into this into this, which is referred to as NPR, the number of permutations of n things taken r at a time. Number of permutations of n things taken r at a time, NPR, with nothing being repeated. Now, what you could do here is, in this NPR, which is like a n into n minus 1 into n minus 2 into n minus 3 into n minus r plus 1 is what you have, n minus r plus 1. You multiply numerator denominator with n minus r factorial. That means the number after this would be n minus r minus 1, which is n minus r, and then into n minus r minus 1 into n minus r minus 2 up to 1. That's n minus r factorial. So multiply numerator denominator with n minus r factorial will give you this, yes or no? So then what's the numerator? N into n minus 1 into n minus 2 into n minus 3 into n minus r into n minus r minus 1 into n minus r minus 2 up to 1. That makes it n factorial. The numerator then becomes n factorial. So the numerator becomes n factorial. This is like n factorial by n minus r factorial. Right? Yes or no? So that's the number of permutations of n different things taken r at a time with nothing being repeated. There is only a single copy of each one of these things available for use to fill out these spaces. The moment you fill out spaces, you are building order. That's the important thing. Remember, each time you try to carry out a count, by filling out spaces and then use the fundamental principle of counting, you're actually building an order, and it will always be a case of permutation. Now, realize that n factorial is n into n minus 1 factorial. N factorial is n into n minus 1 factorial. Now, as a special case, if you put n equal to 1 on both sides, then the left hand side is 1 factorial equal to 1 into 0 factorial, and that gives us 0 factorial equal to 1. That gives you 0 factorial equal to 1. Right? So now we have, suppose, n different things, and I want to create a permutation of n different things taking all at a time. NPN, which is number of permutations of n different things taken all at a time, right? So that's going to be, the numerator is n factorial, the denominator is 0 factorial by putting r equal to n, and the denominator becomes 0 factorial, which is 1. So this simply becomes n factorial. N factorial by 0 factorial is n factorial. So number of permutation of n different things taken all at a time with nothing being repeated is n factorial is n factorial. How about it? Right? Now, so it's like you want to create a flag of 5 colors. You want to create a flag of 5 colors, and the colors given are blue, green, yellow, orange, white. How many flags could be created? Number of permutations of 5 things taken all at a time, 5 at a time. So that's going to be 5 factorial. Suppose you want to create a 3 colored flag, then it's going to be 5p3, in which I'm not allowing repetition of colors. Repetition of colors is not being allowed. Yes or no? Right? So number of permutations of n different things taken all at a time would be n factorial. Number of permutations of n different things taken r at a time is going to be npr, which is n factorial by n minus r factorial. Yes or no? Now, if I have n different things, but then multiple copies of each thing available for use, if I allow repetition, right? N different things. If I have n different things, call them T1, T2, T3, T4, Tn. These are the n different things, right? And there is a bag in which there are large number of T1s there, which therefore T1 could be used multiple number of times. There are large number of T2s, it could be used multiple number of times. So each thing could be used any number of times, say. Each thing could be used any number of times, right? That means repetition allowed. And I want to figure out the number of permutations of these n different things taken r at a time, in which each thing could be used any number of times, So again, what I am seeking is r spaces to be filled out, because it's a case of permutation, so the order is important. So you will have to fill out r spaces in order. These are r spaces. Now, the first space can be filled out in n ways. With any one of the n things, it can be filled out in n ways. Now, once you have filled out the first space with any one of these n things, the second space can still be filled out in n ways. Why? Because I am allowing repetition. So the second space can also be filled out in n ways. The third space can also be filled out in n ways. The rth space can also be filled out in n ways. So the total number of ways in which you could fill out space 1 and space 2 and space 3 and space r with repetition allowed from these n different things is n into n into n into n, which makes it n to power r, with repetition allowed. Yes or no? Now, what I am seeking next is a selection of r things. I want to select r things from these n with order not important. In the earlier case, the order was important. I want to select R things from these N, that means there are N people, and I want to create a committee of R. Obviously, you can't have multiple copies of the same person in a committee, right? So, select R things, and then the order is not important, whether you have selected Mr. Ranjan first and Mr. Das second and Mr. Bhomik third, it does not matter. The order is not important, right? It's just who's selected in the committee, that will be regarded as a way of selection. And then that mode of selection is called a combination, and it's referred to as NCR, which is number of combinations of N different things taken R at a time with repetition not allowed. I'm not allowing for repetition. NCR, right, is what I'm seeking. Now, so it's only about selection. It's about selection. Let's say there are X ways of selecting this. Let's say there are X ways. X is NCR. There are X modes of selection of R people from N available. N ways in which, X ways in which R people could be selected from N available, right? So, let me designate those ways of selection of R people as W1, let's say, is one mode of selection of R people. And this mode of selection of R people, for example, could be T1, T3, T4, T5, T8, T9, T20, etc. Right? They would be R people that is selected, and the order in which they are selected is not important, right? So let's say W1 is one mode of selection of R people. One mode of selection of R people. One mode. This is one way to select. And I am assuming, let's say, that there are X ways in which I could select R people. There are X ways in which I could select R people. The first way of selection of these R people I refer to as W1. The second way of selection of these R people. Now, it will be now a different set of R people. Not entirely different, but even if one person is different in W2 compared to W1, it would be looked upon as a different mode of selection. Right? So, W2, again, second mode of selection of R people. WX, the XH mode of selection of R people. There are X modes of selection of R people from N available. That's NCR, right? You know what I'm saying? So, X ways. So, I'm calling this as NCR. Now, for each of these ways, for example, let's say W1 is one way of selection of R people. One way of selection of R people. This, for example, could be, say, T1, T2, T3, TR, let's say, is one mode of selection of R people. This is one mode of selection of R people. Right? Now, if in this selection, I have to make these people stand in a row. I have to make these people T1, T2, T3, TR stand in a row. There are these R people that I have selected, let's say in way 1, W1, and if I have to make them stand in a row. The selection will not matter whether, in the selection it does not matter whether T2 is here and T1 is there. Right? If I have to make them stand in a row, then the order will be important. Right? This particular mode of selection of R people, if I have to make them stand in a row, then the order in which they come will be important. Right? So then, realize that how many orders can I create out of these R people? R factorial orders, R factorial ways in which I could shuffle them, R factorial ways in which I could shuffle these R people, yes or no? That means first I select R people and now I begin to shuffle them. In how many ways can I shuffle them? R factorial ways, right? So these could be rearranged, mutually rearranged in R factorial ways. Similarly, there are R people in this, there are R people, a different set. Even if one person is different in this set compared to the set, it will be looked upon as a different mode of selection, right? So there are R people in this selection, and again this set, these people could be rearranged amongst each other in R factorial ways. So from selection I am creating, from each of these selections I am creating a permutation, yes or no? I am selecting and then I am rearranging. So essentially after selecting I am permuting, right? So there are R factorial permutations of these people. Then there are again a new set of R people. There are R factorial permutations of this new set of people. There are R factorial permutations of this third set of people. And there are R factorial permutations of this xth set of people. This is the xth set of people. Yes or no? Which means after I select R people and I permute them, I am actually creating permutation of R things from n available. You know? So realize that R people are selected and they are permuted amongst each other. They are permuted amongst each other. They are rearranged amongst each other. In how many ways can you do that? Select and then permute R factorial plus R factorial plus R factorial plus R factorial plus R factorial. How many times? X times. So then X times R factorial actually refers to what? Selecting R people and then permuting them amongst each other, rearranging them amongst each other. And that can be done in X into R factorial ways. But then this by definition is NPR, number of permutations of n things taken R at a time, yes or no? This is actually NPR, number of permutations of n things taken R at a time. So this actually is NPR. Actually, what is it that you do in NPR? One way you can do NPR is by filling out those spaces. The other thing is you select R and then arrange them in those spaces. That's also permutation. So that's what we did. We selected these R things and arranged them in those R spaces in R factorial ways. So I'm actually creating permutation. From each of these ways, W1, W2, W3, Wx, I'm making a selection and then I'm creating a permutation. So R factorial plus R factorial plus R factorial plus R factorial, that is X times R factorial, is number of permutations of n things taken R at a time. Where what is X? X is NCR. Number of ways in which I could select R things. X was what? The number of ways in which I could select R things from these n available, right? So then what does X turn out to be? X turns out to be NPR by R factorial. X then turns out to be NPR by R factorial, which is like n factorial by n minus R factorial by R factorial. And this X was what? Number of ways in which R people could be selected from n available. Number of ways, number of combinations of n things taken R at a time. So this was NCR, number of combinations of n things taken R at a time. Number of combinations of n things taken R at a time, NCR, that's n factorial by n minus R factorial by R factorial, yes or no? Right? Clear? Now, we look at number of permutations of n different things, no, n things in which P are alike and of one kind, Q are alike and of a second kind, R are alike and of a third kind. That means, you can have 20 fruits in which there could be 5 mangoes, 6 apples and 9 oranges. That's what I mean. So these 5 apples, 9, etc. these are things of the same type in multiple numbers available. So now I have number of permutations of n things, not all different. In this n things, there are p things that are identical and of one kind, q things that are identical and of a second kind, r things that are identical and of a third kind, right? And I now want to find the number of permutations of n things in which this is the constitution taken all at a time. Number of permutations of n things, not all different. There are p identical in this, q identical of a second kind, r identical and of a third kind, and I want to take all of them together to create the permutation. Again, if it's a case of permutation, it's about taking n spaces and trying to figure out in how many ways can I fill out those n spaces, and how many ways can I fill out those n spaces, yes or no, taken all at a time, so n spaces. So there are these n spaces. That will give me the permutation, required permutation. Now, there are q of these identical things, p of these identical things, right? And I have to place them in p of these spaces. What I do is, I start allocating, instead of filling out space by space. See, the count is yours, it's up to you how you want to carry out the count. So one way to fill out these spaces is, fill out this space and then this space and then this space and so on and so forth. The other way is, these are your things, p things alike and of one kind, q things alike and of a second kind, and r things alike and of a third kind, constituting this n, right? Now these p things I can allocate to spaces, and then q things I can allocate to these spaces, r things I can allocate to these spaces, right? So now, instead of filling out these spaces one after the other, I start allocating these things to spaces. That means number of ways in which I could allocate p things here and q things here and r things here will give me the number of permutations of these n things of the following kind, of this kind, in which the order would be built in, because it's about filling up spaces. So from these n spaces, you select p spaces. From these n spaces, you just select these p spaces. From n spaces, in how many ways can you only select p spaces? NCP, yes or no? From n spaces, in how many ways can you select p spaces? NCP spaces. And now in these p spaces, fill out the p's. Fill out these p identical things. There is only one way in which you could fill out these identical things in the p spaces. If you are given p spaces and these p identical things, there is only one way in which you could fill out these identical things in those p spaces, right? So then you just select the p spaces and dump these p identical things in those p spaces first. And then, so first you carry out this event, selection of p spaces where these p things could be dumped. And then, how many spaces remain? N minus p spaces remain. In the remaining n minus, from the remaining n minus p spaces, you select q spaces. You select the q spaces and then fill out these q things. There are q identical things in those q spaces, right? So now you have used up p plus q spaces. Now you have used up p plus q spaces. So you must be left with only r spaces. You must be left with r spaces, and in those r spaces you want to dump these r identical things. There is only one way in which you couldn't do that. right? There is only one way in which you could dump R identical things in R spaces. Yes or no? One way. Right? So this then is the number of ways in which you could fill out these spaces from P identical things of one kind, Q identical things of a second kind, R identical things of a third kind. So this will give you the number of permutations of n things taken all at a time, in which P are identical of one kind, Q are identical of a second kind, and R are identical of a third kind. That means P plus Q plus R is n. This would be the required count. This would be the required count, yes or no? This would be the required count. How about it? Which then turns out to be NCP is what? N factorial by n minus p factorial by p factorial, that's NCP, right? N minus p CQ is n minus p factorial by n minus p minus q factorial by q factorial, which then realize that this n minus p factorial will get cancelled with this n minus p factorial, right? And n minus p plus q is actually r. N minus, this will be p plus q, that will be r. So then this turns out to be n factorial by p factorial into q factorial, and then this is r. So r factorial. Number of permutations of n things taken all at a time, in which P are alike and of one kind, Q are alike and of a second kind, R are alike and of a third kind, is n factorial by P factorial into Q factorial into R factorial. Sounds all right? Right? So if it's like three apples, 5 oranges, and 6 apricots, there are 14 things, and you want to find the number of permutations of these 14 things. You want to arrange apples, oranges, apricots, these 14 apples, oranges, apricots in a row. That means number of permutations of these 14 things, in which 3 are alike and of one kind, 5 are alike and of a second kind, 6 are alike and of a third kind, and you want to fill out these spaces. In how many ways can you do that? 14 factorial by 3 factorial into 5 factorial into 6 factorial. That's the number of permutations of 14 things, in which 3 are alike and of one kind, 5 are alike and of a second kind, 6 are alike and of a third kind. Clear? Now, say you start from a point 0, 0, 0 in 3D space. You start from a point 0, 0, 0 in 3D space, the origin. Call it the O, point O. And you want to be able to go to a point P, with coordinates 14, 5, 9. You want to go from O to P. Now, there are certain rules of going from O to P. Let's say somebody prescribes rules of going from O to P. 1. You could move at a time, either parallel to the x-axis, or you could move parallel to the y-axis, or you could move parallel to the x-axis at a time. If you are taking a step in any direction, then that direction has to be either parallel to the x-axis, or parallel to the y-axis, or parallel to the z-axis. right? Not just that, the size of the step is 1 unit at a time. At a time you can't take 2 units in the x direction. You could take only 1 unit in the x direction. After that you could go another 1 unit in the x direction, that's your choice. But at a time you are permitted to take only 1 unit in any one of the 3 directions, x, y or z. And you are allowed to move not backwards. That means if you've already moved 2 units in the x direction, if your coordinates are such at a given instant when x is 2, you can't come backwards. That means you are allowed to move in the positive x direction, in the positive y direction, in the positive z direction, right? Now, in how many ways can you go from O to P? In how many ways can you go from O to P? Realize that the scheme of going from O to P is like taking how many steps? In all, you'll have to take 14 steps parallel to the x direction, not necessarily one after the other. You'll have to take 5 steps parallel to the y direction. You'll have to take 9 steps parallel to the z direction. Yes or no? Right? And it's like out of these 14 steps, you could take first 2 steps parallel to the x direction, then you could take 1 step parallel to the y direction, then you could take 2 steps parallel to the z direction, and so on and so forth. The total number of steps, however, in any order would be 14 plus 5 plus 9, that is 28 steps to be taken in all. 28 steps to be taken in all. Now, the blueprint of going from O to B, let me arrange in 28 spaces. In 28 steps, I'll go from O to P. For example, the first 2 steps could be parallel to the x direction. The next 3 steps could be parallel to the y direction, and so on and so forth. Now, out of these 28 spaces, 14 must be parallel to the x direction, 5 must be parallel to the y direction, 9 must be parallel to the z direction. Yes or no? Right? So now I have to fill out these 28 spaces, number of permutations of 28 things in which 14 are alike and of one kind, 5 are alike and of a second kind, 9 are alike and of a third kind. Yes or no? All steps taken parallel to the x direction would be looked upon as identical. All steps parallel to the y direction could be looked upon as identical. All steps parallel to the z direction could be looked upon as identical, right? So, number of permutations of 28 things in which 14 are alike and of one kind, 5 are alike and of a second kind, 9 are alike and of a third kind. In how many ways can you do that? It's like 28 factorial by 14 factorial, 5 factorial into 9 factorial. Yes or no? Right? Now, some important results used commonly between combinatorics and binomial theorem. Some of them we'll establish algebraically, some we'll establish using combinatorics, right? But then these are very, very useful and very, very commonly used results. One is NCR is NC n minus R. NCR is NC n minus R. That's result number 1. That means number of combinations of n different things taken R at a time, again in which repetition is not allowed, is the same as number of combinations of n things taken n minus R at a time, again in which repetition is not allowed. N different things, right, is the same. How do we establish that? Well, there are n of these things, T1, T2, Gn. Single copy of each of these things. Single copy of each of these things. Now, each time I select R things, each time I select R things from these n, each time I select R things, realize that I am also leaving out n minus R things. Each time I select R things, I am actually leaving out n minus R things. Yes or no? Every time, see, if I select T1, T2, Tr, then the remaining n minus R things are left behind, right? So you can always say that, well, leaving out, it's actually I am selecting n minus R things and leaving out R things. You could also say that, right? So the number of ways in which you could select R things is the number of ways in which you could select n minus R things from n available. Yes or no? Right? So number of combinations of n things taken R at a time is number of combinations of n things taken n minus R at a time, because every selection of R things will lead to one selection of n minus R things. So the number of ways in which I could select R things is the number of ways in which I could select n minus R things from n different things available, in which repetition again is not allowed. Clear? Got me? So that's result number 1. So it's like if I say 20C3, then that's the same as 20C17. Because every time you select things, 3 things, you are actually leaving behind 17 things. So number of ways in which you could select 3 things is the number of ways in which you could select 17 things from 20 different things available. Clear? That's result number 1. NCR is NC n minus R. Result number 2. NCR plus NCR minus 1 is n plus 1 CR. NCR plus NCR minus 1 is n plus 1 CR. Again, we could have established this result algebraically, but let's deploy combinatorics to establish this result. NCR plus NCR minus 1 is n plus 1 CR. Look, there are n different things, n plus 1 different things. T1, T2, T3, Tn plus 1, right? N plus 1 different things. And you want to select R things from these n plus 1 different things. Again, if I am not saying anything, means repetition is not allowed, right? You want to select R things. Number of ways in which you could do that is n plus 1 CR. Number of ways in which you could do that is n plus 1 CR, which is the right hand side of this equation, right? Number of ways in which you could select R things from n plus 1 different available is n plus 1 CR. That's the right hand side of this equation. Now, in these number of ways in which you could select R things from n plus 1 available, right? There are different modes of these selection of R things. Now look at T2 for example. Look at T2 for example. Think of the thing T2. Think of T2 for example. Some of these modes of selection will contain T2, the remaining will not contain T2. All modes of these selection, n plus 1 CR modes of selection of R things, different ways of selection of these R things. Some of these ways will contain T2, the remaining will not contain T2. Yes or no? So then, what I can say is, number of ways in which I could select R things is number of ways in which I could select R things in which T2 is there, plus number of ways in which I could select R things in which T2 is not there. Yes or no? Right? Can I say that this is number of ways in which R things be selected with T2 being there plus number of ways in which T2 is not there. all modes of selection would be such that either T2 is there or T2 is not there. If I add all of them, I will get the total number of ways of selection of R things from n plus 1 available. Yes or no? Are you comfortable with this idea? Right? Okay. Now, number of ways in which T2 is there. Number of ways in which T2 is there. What am I trying to do? From n plus 1 things, I am trying to select R things in which T2 is there for sure. That means T2 is certainly included. So, if I include T2 for sure, then I am no longer obliged to select n plus 1 things. How many things do I need to select? N things. N things is all that I need to select. And from how many things? N things. I need to select how many? There are n available things now because T2 is already included in that selection. So, remaining number of things n. From these n things, how many do I need to select now? R minus 1 things. Why? Because I have already selected T2. So, I am obliged to select a total number of R things. 1 I have already selected. So, I need to select R minus 1 things. From the remaining n, I just need to select R minus 1 things. Yes or no? So, number of cases in which T2 is included for sure. Number of cases in which T2 is included for sure is NC R minus 1. Right? Now, number of cases in which T2 is not there. So, then again, I am excluding the case T2. I am excluding the existence of T2. How many things remain? N things remain. And from this, I still have to select R things because T2 is not selected. I need to select R things. Yes or no? So, then number of ways in which I could do that is NCR. So, these are the number of cases in which T2 is therefore is certainly not there. NCR. These are the cases in which T2 is there. So, n plus 1 CR must be equal to this plus this. Cases in which T2 is there plus number of cases in which T2 is not there. Yes or no? So, n plus 1 CR is NCR plus NCR minus 1. R things have to be selected. R things have to be selected from n plus 1 available, and this is a generalized result. N plus 1 CR is NCR plus NCR minus 1. Got it? Very useful result. Now, say there are n people. Say there are n people. Let's say there are n people. And I want to be able to constitute committees of all possible sizes from these people. These people I want to constitute committees of all possible sizes. The question is, how many committees could be created? The question is, how many committees could be created? Well, first of all, they would be committees with no person. That's one committee, isn't it? A committee with no person is one committee. Notionally, think of it. Arey, sasure, has kahe ko rahe ho? A committee with no person could be looked upon as one committee, right? Then there could be a committee with 2 people, with 1 person. There could be a committee with 2 people. There could be a committee with 3 people. There could be a committee with 4 people. There could be a committee with n people. Yes or no? Now, realize that to constitute a committee, no matter what size it is, let's say this is a committee, between these braces there is a committee. Within these braces there could be no person, there could be 1 person, there could be 2 people, there could be 3 people, there could be all n people, right? Now to create a committee, one way to create a committee is I can go person to person. I can go person to person. For example, I go to P1. In constituting my committee, either I include P1 or I don't include P1. No matter what the size of the committee is, either I include P1 or I don't include P1. So in how many ways can I deal with P1 in my attempt to produce a committee of any size? 2 ways of dealing with P1. Either I include P1 or I don't include P1, yes or no? In my attempt to create a committee, I can either include P1 or I don't include P1. So there are 2 ways of dealing with P1. How about it? Right? 2 ways of dealing with P1. How many ways of dealing with P2? 2 ways. In constituting a committee, no matter what size, there are 2 ways of dealing with P2. Either I include P2 or I don't include P2. There are 2 ways of dealing with P3. There are 2 ways of dealing with Pn. Yes or no? So the total number of ways in which I can deal with P1 and P2 and P3 and Pn will give me the total number of committees that I can create of different sizes. That isn't it? Number of ways in which I can, in my attempt to create a committee, the number of ways in which I could deal with P1 and P2, that means either their inclusion or not their exclusion from the committee, will give me the total number of committees that I can constitute. 2 into 2 into 2 into 2, which makes it 2 to the power n. So I can create 2 to the power n committees, in which there is 1 committee in which there is no one, in which there is 1 committee in which there is no one, there is 1 committee in which there is everyone. Yes or no? These many committees could be created, right? Now, let's start counting differently. Let's start counting the number of committees differently, right? One thing, I hope all of you have understood that there are 2 to the power n committees of various sizes, size 0, size 1, size 2, size 3, size 4, size 5, size n possible. Yes or no? Now, the other way to look at it is to carry out the same count now a little differently. Let me create a committee of size 0. It's like selecting 0 people from n available. In how many ways can I create a committee of size 0? NC0. Selecting no one from n available. Number of ways of selecting no one from n available. There is only one way of selecting, so NC0 will be 1. NC0 will be 1. Then, in how many ways can I create a committee of 1 person? NC1. NC1, number of ways of selecting 1 person from n available, will give me committees of 1 person. NC1 committees of 1 person. How many committees of 2 people? NC2. How many committees of n people? NCn. Yes or no? So the total number of committees of size 0 or size 1 or size 2 or size n, committees of various sizes, total number of committees of various sizes that could be constituted out of these n people is NC0 plus NC1 plus NC2 plus NCn. These are committees of various sizes that could be constituted out of n people, including a committee of size 0, including a committee of size n. But then, that we have already figured out is 2 to the power n. To create a committee, either include a person or not include a person, right? So then, this must be 2 to the power n, total number of committees. So this is another important result. NC0 plus NC1 plus NC2 plus NCn is 2 to the power n, is 2 to the power. Got me? Another result very commonly used very commonly used in combinatorics as well as binomial theorem. Clear? We write it in summation notation as summation NCR r equal to 0 to n as 2 to power n. Now, m plus n CR, m plus n CR. That's another result. M plus NCR is MC0 NCR plus MC1 NCR minus 1 plus MC2 NCR minus 2 up to MCR NC0, MCR NC0. Now, think of this result as follows. Say that there is a class in which there are m plus n students, m plus n students in a class. Out of which there are m boys and n girls. And I want to create a chess team of R members. I want to create a chess team of R members from amongst them. A team of R members. Now, so it's like selecting R people from m plus n available. It's like selecting R people from m plus n available. So, in how many ways can I do that? M plus n CR. That's the number of teams that I can constitute from m plus n students taking R at a time, right? Team of R members. Number of teams of R members that could be made is m plus n CR, right? Now, this could be made in the following way. A team of R people could be either 0 boys and R girls, or 1 boy, R minus 1 girls, or 2 boys, R minus 2 girls, or R boys and 0 girls. Yes or no? So then, one way to select R people is just selecting 0 boys and then selecting R girls. So in how many ways do you select 0 boys? MC 0 ways. And then select R girls from N. In how many ways can you do that? NCR. So in these many ways, you can select 0 boys and R girls for a team. Okay. Or you could select R members with this composition. You could select R members with this composition. Select 1 boy from M available and R minus 1 girls from N available. Right? Yes or no? Nothing. Okay, I mean I have to select R members of the team, right? The various ways in which I could select R members, the various compositions are, one is I select no boy and R girls, I select 1 boy and R minus 1 girls, or I select 2 boys and R minus 2 girls. These are various ways in which I could select R team members from M plus 1 N available. So then, in how many ways can you select 0 boys from M boys, MC0, and so this and this will have to take simultaneously because you want R members, and then R girls from N available could be selected in NCR. So this event of selecting 0 boys and R girls can take place in MC0 into NCR base, or the R member team could be constituted by 1 boy and R minus 1 girls. 1 boy can be selected in MC1 base and R minus 1 girls could be selected in NC R minus base. So this blend could take place in these many ways, or I could have this as my blend, 2 boys and R minus 2 girls. So 2 boys and R minus 2 girls. This is possible. Or R boys and 0 girls can be selected in these many ways. So the number of ways in which I could select R team members is this, in which 0 boys and R girls, or 1 boy and R minus 1 girls, or 2 boys and R minus 2 girls, up to R boys and 0 girls. This is the total number of ways in which I could select R team members from M plus N available. So would you believe that this must be M plus N CR? This must be M plus N CR. So this is another very important result. M plus N CR is this plus this plus this, etc. It's called Vandermont's theorem. It's called Vandermont's theorem. Vandermont's theorem. Right? Useful result. M plus NCR, MC0, NCR, MC1, NCR minus 1, and so on and so forth. Clear? Are you fine with this? The next very important result is R into NCR is N into N minus 1 CR minus 1. Let's establish this result. R into NCR is N into N minus 1 C R minus 1. Clear? Say there is an organization in which there are N people working. There are N people working. N people working in an organization. Refer to them as P1, P2, P3, Pn. From these, you want to create a R member committee. R member committee in which one of them is a manager. From these, you want to create a R member committee with a manager. That means within these R members, one of the R members is a manager. You want to create a R member committee in which one of the R members is a manager. Okay, very simple. First of all, in how many ways can you select R members from N available? NCR, So these many committees could be constituted. These many committees could be constituted from N, taking R at a time. NCR committees could be made with R members. Now, for each of these NCR committees, there are R members in each committee. For each of these committees, there are R members. Any one of the members could be a manager. So then, the number of managers in each committee possible is R. Number of managers in each committee possible is R, because there are R members. Any one of them could be a manager. So first select the committees in NCR ways, and then for each of these committees, there are R ways of selecting a manager. For each of these committees, there are R ways of selecting a manager. So R into NCR will give to me the number of ways in which I could select a R member committee with a manager. That's the left hand side of the equation. Now, I could have also done the following. There are N people. Let me first select the manager. Here I constituted the committee in NCR ways, and then from each of these committees there are R ways of creating a manager. So these many ways of creating a committee with a manager, right? I could have first selected the manager. There are N people. From amongst these N, I can select one manager in N ways, right? Any one of them could have been selected as a manager. So first I select a manager. In how many ways can I select the manager? N ways, right? How many now people remain? N minus 1 people remain. Now I've already selected one. How many do I need to select now? R minus 1. So N minus 1, C R minus 1. First I select the manager in N ways, and then from the remaining N minus 1 people I select R minus 1 in these many ways. So this will be my. So then these two essentially are about the same thing, creating a R member committee with a manager. So they must be the same. So this must be equal to N into N minus 1 C R minus 1. Another very important result. What the hell is this? What is this? हाँ? गर्लफ्रेंड का नाम नहीं है, क्या है, नाम क्या है, पूरा पढ़ के बताओ मेरे को. हाँ, ANAVI, अनावी. ये यहाँ परमुटेशन कॉम्बिनेशन करा रहे हैं, वहां पे तुम गर्लफ्रेंड की बातचीत कर रहे हो. हाँ? तुमने लिखा था और ये अभी देखा है, तो तुम इसकी किताब के साथ चोरी मोरी करते हो. अरे ससुरे, ये सब क्या कर रहे हो? तुम कर लिया या नहीं कर लिया उसका कोई मतलब नहीं है. मेरे ठीक सामने बैठ के दंत मंजनपना कर रहे हो. हाँ, मत करो ये सब. तुम वैसे ठीक से पढ़ाई लिखाई करते हो इसलिए हम तुमको कुछ नहीं बोल रहे, नहीं तो हम फोड़ के रख देते. ठीक है, मत करना ऐसे आगे से. बाहर सारा दिन पड़ा है, गर्लफ्रेंड बॉयफ्रेंड का बात करने का तुमको यही टाइम मिलता है. सोचो जरा, क्या बोले, जनरेशन पूरा डाउन द ड्रेन चला गया. शिट, सो बैड. आई मीन alright, another very important result. This is not related to his girlfriend nor your boyfriend. Alright. और उसकी गर्लफ्रेंड में तुमको कितना इंटरेस्ट है, उसका नाम लिख रहे हो, इतना प्यार मोहब्बत है। हाँ, क्या करते हो यार, तेरे के। छुड़वाना है उससे तो उसे सीधा धमकी उमकी देके छुड़वा लो, बोलो मेरी है आज से। कौन से स्कूल की है? नहीं पता, नाम पता है उसका, यही बोला था। तुम बिरलाई से में कितने साल से हो? हाँ, so the next important result is, आ जाओ तुम ये रिजल्ट प्रूफ करो कॉम्बिनेट्रिक्स से मेरे लिए, यहां आके करोगे, नहीं यही करना होगा, नहीं। तो आगे से ये सब करोगे, ओके। NC1 प्लस 2 into NC2 करो कॉम्बिनेट्रिक्स से रिजल्ट। नहीं करोगे तुमको देखो हम बहुत कुछ बोलेंगे अभी। हाँ। नहीं ठीक है, so don't take load, it's okay. This is another very important result. In fact, this result is used more in binomial theorem than in combinatorics. Not used, in fact, hardly used in combinatorics, but very heavily used in binomial theorem, right? Now, not difficult again, very simple. It's just that you should know how to count, right? Again, think of n people. Hello, huh? Say there are n people. I want to find the number of ways in which I can constitute committees of all possible sizes with a manager in each. A committee of all possible sizes with a manager for each, with a manager for So what I do is, first of all, out of these n people, I can create a manager. First I can select a manager, right? No matter what the size of the committee is, I can select a manager. And that I can do in n ways. So for sure, the moment I select one person and that as the manager, it can't be a committee of size 0. There has to be at least one member in the committee, right? So first I select a manager from n people in n ways, right? Now, how many people remain? N minus 1 people remain. Let's say P1 prime, P2 prime, Pn minus 1 prime are the remaining people, right? Now to create a committee, no matter what the size, either I may select P1 prime or not select P1 prime, select P2 prime or not select P2 prime, select P3 prime or not select P3 prime, select Pn minus 1 prime or not select Pn minus 1 prime, yes or no, right? So how many ways I can deal with P1 prime? Two ways of dealing with each one of them in my attempt to create a committee, yes or no? So that makes it 2 to the power n minus 1. So first I select a manager in n ways, and then the number of committees that I could create from the remaining n minus 1 people is 2 to the power n minus 1. So this will give me what? N into 2 to the power n minus 1 will give me committees of all possible sizes with with one manager. I can have a committee of one person with one manager, committee of two people with one manager, committee of three people amongst whom one is a manager, four people amongst whom one is a manager, and so on and so forth. That's n into 2 to the power n minus 1, right? So then, look at this. I can create a committee of one person in NC1 ways, and that person is the manager himself. If there is one person, then he has to be the manager, right? I can create a committee of two people, and from these two people, any one of them can be the manager. So, two ways of selecting the manager, right? I can create a committee of three people in NC three ways, and the manager could be selected in three ways. I can create a committee of n people, and the manager can be selected in any one of the n ways. So, this gives me committees of all possible sizes. Left hand side gives me committees of all possible sizes with a manager for each committee. Yes or no? And that must also be equal to n into 2 to the power n minus 1. Very useful result. Very, very useful result in fact. Right? Now, this ratio NCR by NCR minus 1 would be very commonly encountered in combinatorics, not in combinatorics, mostly in binomial theorem. NCR by NCR minus 1. Realize that if you simplify it, it will turn out to be NCR is like a n factorial by n minus r factorial by r factorial, right? This is NCR, and NCR minus 1 is n factorial by n minus r plus 1 factorial, r minus 1 factorial. How about it? Right? Make sense? Which is like, now this n factorial will get cancelled. Now n minus r, see one thing, x factorial will be x into x minus 1 factorial, yes or no? So n minus r plus 1 factorial can be looked upon as n minus r plus 1 into this minus 1 factorial. This minus 1 factorial is n minus r factorial into r minus r 1 factorial divided by n minus r factorial into, now this r factorial can be looked upon as r into r minus 1 factorial, right? Yes. What did you not understand? Did you understand that x factorial is x into x minus 1 factorial? So this is x factorial, that's going to be x into this minus 1 factorial is n minus r factorial into r minus 1 factorial. This is n minus r factorial, and r factorial I have written as r into r minus 1 factorial. No? Huh? Sure. Right? Which is like n minus r plus 1 divided by r. Very useful result in binomial theorem, for binomial theorem. Got me? Yet another result, the proof of which will stay pending for a while. Hello? Not you, it was not intended to hit you, it was intended to hit this rugby fellow, rowdy rugby fellow. What the hell is this? Ridiculous. If you could just locate the cap and then I'll treat him right. Have you found the cap? Can you read? Let you go. Amen. One result which I would state without proof, yet a very important result I must say, especially from an examination perspective, is the following. For a given n, NCR assumes different values for different R's. For different R's, NCR will assume different values for a given n. There is a certain value of R for which NCR is a maximum. There is a certain value of R for which NCR assumes the maximum it could. Case 1, when n is even. Case 1, when n is even, NCR is a maximum, assumes a maximum value when R is n by 2. I'll come to the proof later, but for the time being I want you to know this result. NCR, when n is even, will assume a maximum value at R equal to n by 2. When n is odd, NCR assumes a maximum value when R is n minus 1 by 2 or n plus 1 by 2. And it's the same, you will get the same value of NCR for R equal to this or R equal to this. Why? Because see, NCR for this value of R, NC n minus 1 by 2, for R equal to n minus 1 by 2 is actually NC n minus this, NCR is NC n minus R, so NC n minus 1 by 2, but NC n minus 1 by 2 is NC. Realize that 2n minus n plus 1 by 2. So whether it's R equal to n plus 1 by 2 or R equal to n minus 1 by 2, you get the same value of NCR, right? So when n is odd, NCR assumes a maximum at R equal to n minus 1 by 2 or R equal to n plus 1 by 2. Very important result. I want you to take notice of this result. Extremely important result. Another very useful result is the following. The product of R consecutive integers is always divisible by R factorial. The product of R consecutive integers is always divisible by R factorial. Say n plus 1 is an integer, then n plus 2 is the next integer after this, n plus 3 this, n plus R. Do you realize that these are R consecutive integers? These are R consecutive integers. Now when I say that this will always be divisible by R factorial, what does it mean? It means that this divided by R factorial must be a integer, this divided by R factorial must be an integer. So we want to establish that this by R factorial is an integer. Then the problem is solved, right? Now what I do is, I multiply the numerator denominator by n factorial. I multiply the numerator denominator by n factorial. Then, do you realize that this is 1 into 2 into 3 into n plus 1 into n plus 2 into n plus 3 into n plus r. So what's the numerator? N plus r factorial. Is the numerator not n plus r factorial? The numerator is n plus r factorial divided by n factorial into r factorial, right? Which can be written as n plus r CR, isn't it? N plus r CR is n plus r factorial divided by n plus r minus r factorial, which is n factorial, divided by r factorial, which is this. Hey, but number of combinations of n plus r things taken r at a time has to be an integer. What else can it be? Number of combinations of n plus r things taken r at a time has to be an integer. So this is an integer. So the product of r consecutive integers will always be divisible by r factorial, right? Any r consecutive integers, no matter where you start from 30, 31, 32 and you take 50 numbers in the product, that will certainly be divisible by 50 factorial. That will be divisible by 50 factorial. Useful result. I want you to take notice of this, although not very directly used in combinatorics, but used generally in algebra and other branches of mathematics. So taking cognizance of this result could help. Product of r consecutive integers always divisible by r factorial, right? Now, suppose there are n identical toys. Suppose there are, or let's say there are 10 identical toys. 10 identical toys. And there are two children, C1 and C2. There are two children, C1 and C2. You want to be able to distribute. You want to be able to distribute the toys such that each child gets at least one toy. Each child gets at least one toy. Such that each child gets at least one toy. Right? That's how you want to distribute. Let's say, in how many ways can this distribution occur? Okay. One is, you give one toy to C1. You give 2 toys to C2. 8 toys to C1. 3, 7, 9, 1. This is one mode of distribution. This is another mode of distribution. This is the third mode of distribution. This is the 9. So there are 9 ways in which 10 identical toys, there are 9 ways in which 10 identical toys could be distributed amongst 2 children, with each child getting at least one toy. With each child getting at least one toy. Now, you could also look upon this as following. C1, let's say, gets X toys. C2 gets Y toys. Then X plus Y must add up to 10. Where X and Y are natural numbers. X and Y are natural numbers, yes or no? So essentially, what are we seeking? 1, 9 equal to 10, that's one solution to this equation. That's one mode of distribution. 2, 8, 2 and 8 is another solution to this equation, which will give you another mode of distribution of the 10 toys. 3, 7 is yet another solution to this equation, giving you a third mode of distribution of 10 toys to 2 children, and so on and so forth. So then, what are these 9 ways? these 9 ways, essentially the number of natural number solutions to this equation gives me what? Number of natural number solutions to this equation. Number of natural number solutions to this equation will give me the number of ways in which 10 toys could be distributed amongst 2 children with each child getting at least 1. Why did I say natural number solutions to this equation? Because x and y would have to be at least 1. They can't be 0. If it's 0, then it's not natural number, it's full number, right? So the number of solutions to this equation in natural numbers, number of solutions to this equation in natural numbers will give me the number of ways of distributing the 10 identical toys to 2 children. Is that alright? Do you understand this? Number of natural number solutions to this equation will give you the number of ways of distributing 10 identical toys to 2 children, right? Now, let me generalize this issue. N identical toys and our children. N identical toys and our children, with each child getting at least 1 toy. So what are we seeking? Number of ways of distributing n identical things amongst our different people, with each person getting at least 1 toy. You know what I am saying? Number of ways of distributing n identical things to our people, with each person getting at least 1 of those things, at least 1 thing, right? So let's build a blueprint of this. Distribute n identical things amongst our people, with each getting at least 1 thing, with each getting at least 1 thing. We want to distribute n identical things to our people, with each getting at least 1 thing, right? These are n people, or our people, sorry, these are our people, and we have n identical things. That means n copies of T, for example, n copies of, these are n identical things, T, etc. And I want to distribute these to the R people, right? So let's say one mode of distribution is where P1 gets x1, P2 gets x2, P3 gets x3, and PR gets XR things, and all of these must add up to n. That means one mode of distribution would be one solution in natural numbers to this equation. This could be 1, this could be 2, this could be 1, this could be 3, this could be 4, this could be 1, and so on and so forth. All of these must add up to n, right? That means every time you arrive at a natural number solution to this equation, that means a set of values x1, x2, x3, xr, all natural numbers that add up to n, you get one mode of distribution of these n things amongst R people. So what are you seeking? You are seeking the number of natural number solutions to this equation. What are you seeking for this distribution? Number of natural number solutions to this equation, right? So what we are seeking is number of natural number solutions will give the required number of ways, of distributing n identical things to r people, with each person getting at least 1. The very fact that all these xi's are natural numbers will cause each person to get at least one thing, because the least natural number is 1, right? Are you all there with me? So, now we have defined our problem, we know what exactly we are up to. We want to find the number of natural number solutions to this equation, and each mode of a natural number solution to this equation would be one way to distribute n things to r people, and the number of sets of natural number solutions to this will give me the number of ways in which I could distribute n things amongst r people, with each person getting at least one thing. I hope all of you have understood this. Yash, Devta? Huh? So, let's figure out what to do. X1 plus x2 plus x3 plus xr is n, right? Where the xi's can assume values like 1, 2, 3, etc. These are the values that xi can assume. These are the values that xi can assume, right? Now, n actually could be written as sum of n ones, yes or no? 1 plus 1 plus 1 plus 1, n times is n, right? So I do the following. N, right? There are n ones. So far so good, yes or no? Let's say when I write n this way, how many pluses do I encounter? N minus 1 pluses. If there are 2 ones, there is 1 plus. If there are 3 ones, there are 2 pluses. If there are 4 ones, there are 3 pluses. So if there are n ones, how many pluses prevail? N minus 1 pluses. Let's say wherever there is a plus, I could create a tower. Right? Wherever there is a plus, it's a legitimate location of creating a tower. Right? So let's say I create a tower here, one tower, T1. Now if I create one tower at a plus, how many regions am I producing? 2 regions. One to the left of the tower, one to the right of the tower. There are 2 regions. Now sum of ones in region 1 plus sum of ones in region 2 will still be n, right? Yes or no? So with one tower, 2 regions are created. No matter where this tower is, as long as you are placing the tower at a point where there is a plus, with a single tower there are 2 regions produced. Sum of the ones in each region will still add up to n. Suppose I create 2 towers. How many regions am I producing? 3 regions. Again, sum of ones in region 1 plus sum of ones in region 2 plus sum of ones in region 3 will still add up to, and that basic fact will not be disturbed. Right? I create another tower. How many regions am I producing? I create 4 towers. How many regions am I producing? 5. If I am creating R minus 1 towers, how many regions am I producing? R regions, right? So for R towers, R minus 1 regions could be produced. With R minus 1 towers, with R minus 1 towers, R regions could be produced. With R minus 1 towers, R regions could be generated. Yes or no? Sum of ones of region 1 plus sum of ones of region 2 plus sum of ones of region 3 plus sum of ones of region 4 plus sum of ones of region R will still add up to n. Hey, do you realize that every time I erect R minus 1 towers at the location where there are pluses, I am actually creating a solution set to this equation. Why? Because now I can look upon, let's say, x1 as 2, I could look upon x2 as 2, I can look upon x3 for example as 1, I can look upon x4 as 2, I can look upon xr as 3. Yes or no? Have I not created a solution set to this equation? x1 plus x2 plus xr equal to n. So every time I construct R minus 1 towers, at these n minus 1 available locations, I end up creating one solution set in natural numbers to the mother equation. Yes or no? Right? You know what I am saying? So the number of ways in which I could create or erect R minus 1 towers from n minus 1 legitimate locations will give me the number of natural number solutions to this equation. You know what I am saying? Each mode of construction of R minus 1 towers, leads to one solution set of the mother equation. Do you see that? So the number of ways in which R minus 1 towers could be constructed in n minus 1 locations will give me the number of natural number solutions to the mother equation. That means constructing towers, R minus 1 towers is like selecting R minus 1 pluses, from how many available? From n minus 1 available. So in how many ways can I construct R minus 1 towers? From n minus 1 available positions, the towers could be constructed, R minus 1 towers could be constructed in n minus 1 C R minus 1 ways. Yes or no? So these many ways of constructing the R minus 1 towers, and therefore these many natural number solutions to the mother equation. So that's the solution. So this would give me the number of natural number solutions to this equation, and will therefore give me what? The number of ways in which n identical things be distributed amongst R people such that each person gets at least 1. N minus 1 C R minus 1. Okay, I said every time you construct R minus 1 towers, you get R regions. Each region could be looked upon as a xi. So then, let's say in this case, for the mode that I have shown, have I not got a solution set to the mother equation? x1 could be looked upon as 2, x2 could be looked upon as 3, x3 1, x4 2, xr 3, right? So every time you construct R minus 1 towers, you get one solution to the mother equation. So number of ways in which you could construct R minus 1 towers will give you the required number of solutions, right? In no. So how many ways can you construct R minus 1 towers from n minus 1 positions? It's like from n minus 1 positions you will have to select R minus 1 positions, वहां जाके फिर मिस्त्री लगा दोगे तो टावर्स बन जाएगा, फिर जाके अंदर रहना आराम से. बात समझ रहे हो? वो सब मत करना, सिर्फ प्रॉब्लम समझना, right? So the number of ways in which R minus 1 towers could be constructed from n minus 1 positions is n minus 1 C R minus 1, and each mode of construction of R minus 1 towers will give you one solution. And how many modes of construction of R minus 1 towers? N minus 1 C R minus 1. So this will give you the number of ways. N minus 1 C R minus 1 will give you the number of ways of distributing n identical things amongst R people, so that each person gets at least one thing. Okay? Even the two towers that are closest to each other would have at least one. So this mode of construction of tower will ensure that any xi would be at least 1, isn't it? इसीलिए tower ऐसा बनाओगे. You got me? So this is the method of construction of towers. Now don't quote me anywhere for this. This is my figment of my imagination. So never talk about it as towers. In my class, you can refer to this as the method of towers. But otherwise, you can give any other name that you like. So, but this is a very important concept, and this is the foundation to a more sophisticated concept. We will elaborate on this concept down the line, and we'll create wings around this concept, right? More variations, but then this is the foundation. If you've understood this idea, then the rest will follow suit. It's not going to be difficult. You got my point? Rugby? अगली बार से करा ना ऐसा तो पता है मैं क्या करूंगा? Do you want me to spell it out publicly? I can be atrocious, very atrocious. ठीक है? So next time ना, if you are at all in my class at any point of time, you better observe the conduct that I expect out of you. Otherwise, nothing less than being castrated would take place. Intellectual castration is what I would deploy upon you. Understand this right now, right here, and for all times. Got me? Don't do it again. There is a T20 and I have to go. What? भैया इसका वेरिएशंस करूंगा ससुर जी बोला हूं ना देयर आर मोर वेरिएशंस अराउंड दिस आई कैन इवन डिस्ट्रीब्यूट टॉयज अमंग चिल्ड्रन ताकि एक बच्चा रोने भी लगे उसको टॉय नहीं मिला वो सारा केसेस कंसीडर करूंगा जब मैं बोल रहा हूं तो थोड़ा तो पेशेंस रखो जो चीज बता रहा हूं वो समझने का कोशिश नहीं करे ही करके हंस रहे हो बैठ पागल आदमी हाँ